I mean, imagine you're writing a SQL query for like a critical production system. You type out select from users where status active, you hit execute, and the database returns a list of 100 users.
Right. Highly predictable.
Exactly. But then a minute later, without a single byte of underlying data actually changing, you run that exact same query again, and this time it returns a completely different list of users. Or, worse, it confidently hands you back a JSON payload detailing the biography of some 17th century French king.
Yeah, as a back-end engineer, your hair would just be on fire at that
Oh,
point.
completely. You would immediately assume the memory is corrupted or, I don't know, the load balancer is routing you to a staging environment because we are trained to expect mechanical precision, right?
Yeah,
You write a function, you pass it an input payload, and you receive a highly predictable, entirely deterministic output. That's the bedrock of software engineering.
it is. And that expectation of absolute determinism is exactly why the transition into building with large language models feels so jarring for experienced developers.
Yeah, jarring is a good word for it.
Because in a classical back-end architecture, a REST API is a rigidly defined contract. If a request fails, you get a 4xx or 5xx status code, and you get a stack trace, pointing to the precise line of code where the logic broke. We find a lot of comfort in that visibility.
Oh, absolutely.
But the moment you route a user prompt into a generative AI model, that diagnostic X-ray machine just shatters, you are suddenly handing control over to a system that is inherently, well, probabilistic.
Which is the core reason we are doing this today. So I want to welcome you, the listener, especially if you are a developer, an architect, or a backend engineer who is suddenly being asked to, integrate AI into your company's core products. Welcome to a custom-tailored deep dive into the underlying mechanics of foundation models.
It's a much-needed deep dive, I think.
I agree. Our mission today is to take the black box out of these AI APIs. We are going to deconstruct the math, the architecture, and the training recipes to show you exactly how these systems operate from first principles. And we are basing our entire roadmap today on the insights from Chip Huyen's book, AI Engineering, specifically diving into the chapter on understanding foundation models.
Because treating a foundation model like a standard API endpoint is just a recipe for catastrophic system failures.
Yeah, it really is.
You cannot build robust, fault-tolerant applications on top of these models unless you actually understand the forces governing their behavior. So we need to explore the shift from traditional machine learning to AI engineering, analyze the structural realities of the data these models ingest, and then mathematically pop the hood on the transformer architecture.
And we are not stopping there. Once we break down the transformer and, its new rivals that are attempting to solve its massive hardware bottlenecks, we are going to look at the post-training phase.
Right, the really fascinating part.
Yeah. We will demystify how a giant autocomplete engine is mathematically forced into becoming a conversational assistant through fine-tuning. And finally, we'll look at the exact split second of token sampling that dictates why these models hallucinate.
The journey from raw, unstructured internet data all the way to a probabilistically generated API response is fascinating, especially when you view it through the lens of system constraints and compute budgets.
So before we even get to the architecture of the model itself, we really need to address the structural industry shift. Because 10 years ago, if a company wanted to add an AI feature, let's say, a recommendation engine or a fraud detection filter, the backend team would collaborate with data scientists to build a bespoke model.
Exactly. It was highly custom.
But today, you are mostly just plugging your application into massive, pre-trained behemoths hosted by a third party. So why did the entire workflow of an AI engineer suddenly flip upside down?
Well, it comes down to the sheer economics of scale. In the traditional machine learning paradigm, the workflow was intensely sequential and, like you said, hyper-customized. You identified a business problem, you spent months gathering a highly specific clean data set, you trained a model from scratch on that data, and only after validating it did you build the product around it.
So the flow was data, then model, then product.
Right, and a model trained to flag fraudulent credit card transactions was highly efficient at that one task, but it possessed absolutely zero capability to, say, summarize an email or translate text.
It was highly specialized, meaning you needed a completely different model and a completely different training pipeline for every single feature in your application.
And that simply doesn't scale for complex multimodal applications. What the industry discovered is that as you scale up the sheer number of parameters in a neural network, the billions of internal weights and connections, the model's capacity to learn general broad patterns increases exponentially.
But there's a catch, right?
A massive one. To fulfill the potential of a massive parameter count, the model demands an astronomical volume of training data and just an unthinkable amount of compute.
Yeah.
We're talking about tens of thousands of specialized enterprise GPUs running continuously for months.
Which is wild to even think about.
Yeah. The cost of training a state-of-the-art foundation model from scratch today is in the tens or even hundreds of millions of dollars. Very few organizations have the hardware infrastructure to do that.
Which forces the paradigm shift. We rely on a handful of tech giants to build the foundation, and we build our products on top of it.
Which flips the workflow to product, then data, then model. You start by building the product first, rapidly prototyping an application by simply prompting a general-purpose API. You test it to see if the product shows promise.
And if it doesn't, you just move on.
Exactly. Only if the user experience validates the concept do you then invest time in curating specialized data to fine-tune a smaller, custom model, to bring your latency and hosting costs down.
Right. But relying on those giant pre-trained models brings us to a massive vulnerability that back-end engineers really need to understand, and that's the pre-training data itself. Because if these foundation models have an insatiable appetite for data, they can't just be trained on clean proprietary databases, can they?
No, not at all. Model developers essentially have to unleash web scrapers to download the entire public internet.
The whole thing.
They scrape everything. Billions of web pages, digitized libraries, code repositories, social media forums, comment sections. It is a completely indiscriminate vacuuming of human digital artifacts.
Okay, let's unpack this, because using pre-training data from the public internet sounds like populating a production database by just blindly accepting every user's form submission without sanitizing the inputs.
That's a terrifying thought.
It is. We're feeding the model a giant, unfiltered smoothie of the web, whether the original authors consented or not. It includes Wikipedia and MIT research papers, sure, but it also includes conspiracy forums, extreme toxicity, and deeply flawed code snippets. No wonder we have to clean it up later.
The database analogy is highly accurate here. The foundation model is fundamentally a statistical mirror of its training data. So before any later safety alignment is applied, a raw-based model is fully capable of outputting heavily biased, racist, sexist, or completely fabricated content simply because it mathematically learned the statistical patterns of those behaviors from the raw web data.
It doesn't actually know what it's saying.
Right. It doesn't have a concept of truth. It just has a concept of statistical frequency.
And the crazy part is people are actively trying to manipulate that statistical frequency. The book mentions this growing trend of intentional data poisoning.
Oh, yeah. Because the entire tech ecosystem knows that future generations of foundation models will be trained by scraping the public internet. We are seeing coordinated efforts to purposefully post specific narratives online.
Like planting seeds.
Exactly. Individuals and organizations are seeding forums and websites with text, hoping it gets indexed by the web scrapers and baked into the neural weights of the next model.
It's basically an evolution of SEO. Instead of trying to trick Google's search algorithm to rank your hyperlink higher, you are attempting to mathematically infect the worldview of the AI itself. If you can poison the training data, you can subtly influence the answers that millions of users will eventually receive when they query the model.
And that reality is the exact reason why curation and later alignment are so vital. It simply cannot deploy a raw-based model into an enterprise environment.
Oh.
But, before we get to how we align and fix the model, we have to talk about another massive architectural decision for developers, which is licensing.
Right. Because when you decide to pull a model off the shelf to build your application, you have to navigate a maze of terminology, particularly around the term open source.
Yeah, and in standard software engineering, open source is a sacred, well-defined concept. You get the compiled binary, but you also get the source code. You can inspect it, modify it, compile it yourself, and usually use it commercially without restrictions.
But in the AI space, that term has been heavily co-opted, hasn't it?
Very much so. The text is very clear that we need to separate traditional open source from what is more accurately called open weights.
Open weights.
Yes. When a company like Meta releases a massive model, they're often releasing open weights. They give you the final compiled matrix of billions of parameter numbers. You can download those numbers and run the model on your own servers, giving you privacy and control over the inference process.
But they deliberately withhold the training data, the curation scripts, and the source code used to train it. So they basically hide the database.
Exactly. And they do that to avoid public scrutiny over exactly whose copyrighted books they scraped, or to hide the proprietary secret sauce of their data filtering algorithms.
Yeah.
But it's not just the missing training code. The licenses attached to these open weights models contain massive traps for unwary companies.
Yeah, you have to read the licenses meticulously. I mean, Meta's Llama 2 and Llama 3 are prime examples of this. They are incredibly powerful and they are free to download, which obviously makes them very attractive for startups.
Right, very tempting.
But they use a custom community license, not an open source initiative approved license. That custom license allows commercial use, but with a structural trapdoor. If your application scales and surpasses 700 million monthly active users, your license automatically terminates.
That vanishes.
Yep. You have to go to Meta and beg for a custom commercial agreement, which they have the absolute right to deny. Let's play that out from an architectural standpoint. Imagine you are a startup. You build your entire backend infrastructure around Llama 3. You write custom prompt wrappers. You optimize your GPU clusters for Llama's specific tensor parallel requirements. You build your vector database embedding strategies around it.
You're fully locked in.
It's fully locked in.
Fine.
Then your consumer app goes viral. You hit that 700 million user mark. Meta looks at you, sees you as a competitor to their own consumer products, and denies your license. Your entire core product is suddenly illegal to operate.
It's game over.
Ripping out the core intelligence layer of an application at that scale and swapping it for a different model would be an engineering nightmare. It would require a massive system rewrite.
Which is exactly why the license exists, to protect the tech giant from having another massive player, like Apple or an explosive startup, cannibalize their market using their own free research. Furthermore, the Llama licenses contain strict clauses explicitly forbidding model distillation.
Right, model distillation.
Yeah, it's a highly popular technique where a developer uses the outputs of a massive smart model like Llama 370B to automatically generate synthetic training data to teach a much smaller, cheaper model to do a specific task. Meta's license bans you from using Llama to train any competing model.
So if you want true freedom, where do you actually look?
You look for models released under genuine, permissive open-source licenses, like the Apache 2.0 license. Google's Gemma models and Mistral's initial models were released under Apache 2.0. That license allows commercial use without arbitrary user caps and permits you to use the model for distillation and synthetic data generation.
Choosing between a restricted open weights license and a true Apache 2.0 license really is the very first architectural decision an AI engineer must make. Okay, so the landscape is set. We understand the data pipeline, the raw internet scraping, and the licensing minefield. Now we really need to dive into the actual engine. How does a foundation model physically process all this data? We have to dissect the transformer architecture.
The transformer. Introduced in the 2017 paper, Attention is All You Need, it is the singular architectural breakthrough that created the modern generative AI era. But its brilliance only makes sense if we first examine the critical flaws of the system it replaced.
The older sect-seq models.
Right, the sequence-to-sequence models, primarily built on recurrent neural networks, or RNNs.
Let's isolate the RNN for a second. If I fed a paragraph of text into an old RNN, how did it process the data?
It processed the data strictly sequentially, exactly as a human reads. It would ingest the first token, perform a matrix multiplication to update its internal hidden state, then ingest the second token, update the state again, and repeat this process linearly through the entire sequence.
Which created massive bottlenecks. First, the sequential nature meant it was incredibly slow to train, right? Because you couldn't process the input in parallel. You had to wait for token 1 to finish before processing token 2.
Exactly. Which leaves modern GPUs, which are explicitly designed to do thousands of calculations simultaneously, sitting mostly idle.
What a waste of compute.
Yeah. But the second bottleneck was far more destructive to the model's intelligence. As the RNN processed the sequence, it was forced to compress the meaning of all previously read tokens into a single, fixed-size vector called the final hidden state. When the model reached the end of the prompt and needed to start generating a response, the only context it had access to was that single, highly compressed vector.
I love the book's analogy here. It's like, imagine I hand you a dense 500-page textbook on quantum mechanics, but instead of letting you keep the book, I force you to read it once and compress all your knowledge into a single one-paragraph summary.
Good luck with that.
Right. Then I take the book away and I start asking you highly specific, deeply technical questions about a minor formula buried in a footnote on page 342.
You would fail. Because no matter how perfectly crafted the summary paragraph is, a fixed-size representation simply cannot retain the granular details of a massive sequence. The compression inherently destroys localized context.
Which is why early translation models would start strong in the first sentence but completely lose the plot by the third paragraph.
Exactly. The transformer architecture obliterated this compression bottleneck by splitting the inference process into two distinct, highly optimized phases: the prefill phase and the decode phase.
Okay, let's break those apart. How does the prefill phase solve the sequential reading problem?
During the prefill phase, the transformer abandons sequential reading entirely. When you send a prompt via the API, the model ingests every single token of that prompt simultaneously. It processes the entire sequence in parallel across the GPU cores, mapping out the initial mathematical representations of every word at the exact same time.
Wait, if it ingests all the input tokens simultaneously in parallel, how does it know the order of the words? I mean, if I send "the dog bit the man" versus "the man bit the dog," those are the exact same words, ingested simultaneously. In a traditional database, we rely on an auto-incrementing ID or a timestamp to maintain order.
That is a brilliant observation. Because the transformer processes everything at once, it inherently lacks a sense of sequence. To fix this, the architecture injects positional encoding.
Positional encoding.
That's right. Before the parallel processing begins, the model mathematically adds a unique signal, essentially a highly complex, high-dimensional timestamp to the vector of each word. This positional vector tells the model, this token is in position 1, this token is in position 2.
Oh, that's clever.
So even though they are processed at the same time, the model's math retains the knowledge of their absolute and relative positions in the sentence.
Okay, so the prefill phase ingests everything simultaneously, applying positional encodings and utilizing the full parallel power of the GPU. Then we shift into the decode phase, which is where the model actually starts talking back to us.
And the decode phase reverts back to being sequential. The model generates one token, appends that new token to the context window, and then runs the entire process again to predict the next token.
It generates the response token by token, syllable by syllable.
But the true magic, the mechanism that permanently solved the textbook summary problem, operates inside both of these phases, and that's the attention mechanism.
The core engine. To explain the attention mechanism to a back-end developer, we really have to talk in terms of database retrieval. The attention mechanism operates by dynamically generating 3 specific vectors for every single token in the sequence: the query, the key, and the value. Q, K, and V.
Let's define their conceptual roles before we look at the linear algebra. Sure. The query vector, or Q, represents the current state of the model actively looking for information. It is the token asking, what context do I need right now? The key vector, K, represents the identity or the label of a previous token. It says, I contain this specific type of information.
Like an index.
Exactly. And the value vector, V, is the actual learned semantic content of that previous token.
Okay, here's where it gets really interesting for you as a back-end engineer. If we think of this like a database, the query is your SQL statement, right? You are actively querying the system for relevance. The key is the indexed column in your database table, the metadata that the system stands to find a match, and the value is the actual row data, the payload that gets returned when a match is found.
Functionally, that is a superb mental model. But the mathematical implementation is where the transformer diverges radically from a deterministic database.
Right, because it's not binary.
Exactly. In PostgreSQL or MySQL, an SQL query returns a binary result. The row either matches the where clause or it doesn't. If the ID is 5, you get row 5 and only row 5. The transformer's attention mechanism does not perform binary matching. It performs probabilistic weighted blending.
But instead of returning a single matched row, the transformer returns a probabilistic weighted blend of all rows based on relevance. How does that math actually execute? When the model is trying to figure out what word comes next, how does it query the past?
It uses the dot product. During generation, the model takes the query vector of the current token and calculates the dot product against the key vector of every single previous token in the entire context window.
Okay, geometry time.
Right. In high-dimensional geometry, calculating the dot product of two vectors gives you a measure of their similarity or alignment. If the query vector of the current token and the key vector of a past token are pointing in the same general direction in the multidimensional space, the resulting dot product score will be a high positive number.
So a higher dot product score fundamentally means the model pays more attention to that specific token's value vector. It means the model has learned that the current token heavily depends on the context of that specific past token.
Exactly. The model runs this massive matrix multiplication, computing the dot product between the current query and every single passed key. But raw dot product scores can swing wildly in magnitude. So the architecture applies a function called softmax.
Ah, softmax. What does that do?
The softmax function takes that massive list of raw scores and mathematically squashes them into a normalized probability distribution that perfectly sums up to 100%.
Oh, I see. It normalizes those dot product scores into usable probabilities. So after running softmax, the model might determine that for the current token, it needs to pay 60% attention to token number 5, 20% attention to token number 12, 5% to token number 20, and essentially 0% to the words the and scattered throughout the prompt.
Precisely. And this is where the value vectors finally come into play. Instead of returning a single matched row like a database, the transformer creates a custom, probabilistically weighted blend of the entire sequence. It multiplies the value vector of each passed token by its assigned softmax percentage.
So token 5's value vector is multiplied by 0.60.
Yes. Token 12's by 0.20 and so on. It then adds all of those scaled value vectors together to produce a single, highly customized context vector for that specific generation step.
The elegance of that is just staggering. It mathematically guarantees that the model never has to rely on a compressed summary. At every single step of generation, the model dynamically queries the entire history of the document, assigns a relevance percentage to every single word, and blends their underlying meaning together. What is the actual formula from the paper?
The famous equation is attention, QKKAV equals softmax, QKT is the score TDV.
Okay, let's parse that. QKT is the dot product matrix multiplication of the queries and the keys.
Correct. But notice the division by the square root of D.
Right. Y divide by D.
The variable D represents the dimension size of the vectors. If your vectors are 4086 dimensions long, the dot product of two vectors that size can produce an astronomically large number. If you feed numbers that large into a softmax function, the function gets pushed into its extreme flat regions.
And what happens then?
The gradients become vanishingly small, causing the training process to completely stall. Dividing by the square root of the dimension size acts as a scaling factor to keep the variance of the numbers stable, allowing the neural network to learn efficiently. After scaling, you apply softmax for the percentages and multiply by V, the values matrix.
But the architecture doesn't just run this formula once per layer, does it? Because the book details multi-headed attention. Why does the model need multiple heads?
Because human language is infinitely multidimensional. A single word in a sentence has a grammatical relationship to the verb, a semantic relationship to the subject, an emotional tone, and a spatial relationship. If the model only had one single attention mechanism, it would be forced to mathematically average all of those distinct relationships into one muddled query. Multi-headed attention solves this by splitting the matrix.
Let's ground this with the Llama 2 architecture from the text. Llama 2, the 7 billion parameter version, has a hidden dimension size of 4096. So originally, every token is represented by a vector of 4096 floating point numbers.
Yes, but Llama 2 uses 32 independent attention heads. So before running the attention math, it slices that 4096 dimension vector into 32 smaller segments. 4096 divided by 32 is 128.
This means each of the 32 attention heads gets a 128 dimension vector to look at different parts of the context simultaneously.
Exactly, so they operate in parallel. Head number 1 might learn to query the context purely for subject-verb agreement. Head number 2 might specialize in tracking the sentiment or the sarcasm in the prompt. Head number 3 looks for numerical references.
They all run the exact same softmax formula simultaneously, completely independently of each other.
And once all 32 heads have finished their localized attention blending, the architecture concatenates those 32 smaller vectors back together into the original 496 dimension size, passes it through a feed-forward neural network layer, and moves to the next layer of the model to do it all again.
And this parallel processing is why GPUs are required.
Oh, absolutely. This massive, embarrassingly parallel matrix multiplication is the exact reason why we absolutely must execute these models on high-end GPUs, which are physically designed with thousands of ALU cores to process parallel vector math.
Okay, the math is beautiful. The multi-headed attention perfectly solves the sequential bottleneck and the loss of context. But as a back-end engineer, whenever an architect pitches me a system that sounds completely perfect, my immediate reaction is to start looking for the hidden latency traps, the unbounded memory bloat or the scaling cliffs. And the transformer has a massive one, doesn't it?
It does. It possesses a severe architectural limitation known as the KV cache bottleneck. And understanding of this bottleneck is absolutely critical for any developer trying to calculate API costs or manage server latency.
Let's trace the logic on this. During the decode phase, the model is generating one new token at a time. But to run the attention math for that new token, it has to calculate the dot product against the key and value vectors of every single previous token in the conversation.
Exactly. Now, if the model had to mathematically recompute the key and value vectors for all the old tokens every single time it generated a new word, the inference speed would slow to a crawl. It would be computationally devastating.
Right.
To prevent this, AI engineers implemented a caching mechanism. When a token is processed during the prefill phase, its key and value vectors are saved directly into the GPU's high-speed memory, the VRAM. This is the KV cache.
Oh, I see.
When generating the next token, the model just retrieves the historical vectors from memory instead of recalculating them.
That makes perfect sense. Caching immutable data to save compute cycles is backend 101. We do it constantly with Redis or Memcached. What is the catastrophic problem here?
The problem is the scaling curve, because every single token in the context window gets its own key and value vector, and those vectors contain thousands of floating point numbers across dozens of layers. The physical memory required to store the KV cache grows quadratically as the sequence gets longer.
Let's emphasize that. Quadratic growth. This means context length isn't just a premium feature you toggle on, it is an exponential cost multiplier. If I am an engineer and I decide to send a 20-page document to the API instead of a 10-page document, the compute cost doesn't just double. Doubling the input quadruples the computational workload.
Exactly. Every single new token has to mathematically query every single other token. As the sequence gets longer, the matrix multiplication becomes astronomical, and the KV cache bloats until it entirely consumes the GPU's VRAM.
Wow.
An NVIDIA H100 GPU has 80 gigabytes of VRAM. That sounds like a massive amount of memory, but if you attempt to process a 100,000 token document through a large transformer model, the KV cache alone will overflow that 80 gigabytes, crashing the system with an out-of-memory error.
So this makes extending context lengths incredibly hard and memory intensive.
Yes, this quadratic scaling is the fundamental reason why it is so difficult and economically punishing to build and host models with massive context windows.
Which means the research community is highly incentivized to find a way to dethrone the transformer. We need an architecture that scales linearly, where doubling the document size only doubles the cost. The text highlights a new class of architectures attempting to do exactly this: state space models, or SSMs. Let's look at the first contender, Mamba.
Mamba is a phenomenal breakthrough. It is designed from the ground up as a linear time sequence model. It fundamentally breaks the quadratic curse of the attention mechanism. When you process data through Mamba, the inference computation scales linearly with the sequence length.
That's huge.
It allows a Mamba model to comfortably ingest sequences of up to 1 million tokens without the memory bloat that would destroy a transformer.
But does it actually hold its own intellectually? Because the old RNN scaled sequentially too, but it was too stupid to remember a textbook summary.
That is the magic of Mamba. The researchers demonstrated that a 3 billion parameter Mamba model not only outperformed traditional transformers of the same size, but it actually matches the language modeling performance of transformers twice its size. It manages to compress the state efficiently without suffering the catastrophic memory loss of the old RNNs.
Okay, but then there's Jamba, which takes a different approach. It doesn't throw the transformer away entirely, does it?
No, Jamba is a hybrid architecture. The developers of Jamba recognized a reality. While Mamba is incredibly efficient, the transformer's attention mechanism is still mathematically superior for certain types of highly complex, localized reasoning. So Jamba interleaves the two. It stacks blocks of traditional transformer layers with blocks of Mamba layers.
A Frankenstein architecture to get the best of both worlds. The specs on Jamba are wild, though.
It is a massive 52 billion parameter model. However, it utilizes a technique called mixture of experts, or MOE.
Mixture of experts, how does that work?
In a MOE model, the neural network is divided into specialized subnetworks, or experts. During generation, a routing algorithm determines which specific experts are best suited for the current token and only activates those parts of the network. So, while Jamba has 52 billion parameters stored in memory, only 12 billion parameters are actually active and computing at any given time.
Which brings us to the ultimate deployment flex of Jamba. Because it combines Mamba's linear scaling with the sparse activation of mixture of experts, the entire 52 billion parameter model is specifically engineered to fit onto a single standard 80 gigabyte enterprise GPU while maintaining a massive 256,000 token context window.
Right. Attempting to fit a 256K context window on a pure 50 billion parameter transformer on a single GPU would be physically impossible due to the KV cache explosion.
Okay, here's where I have to push back. So what does this all mean for us? If Mamba scales linearly and solves the memory bloat, and Jamba can compress a massive context window onto a single GPU, why are we still overwhelmingly using transformers? Is it just industry inertia? When a back-end technology proves to be exponentially cheaper and faster, the industry usually migrates ruthlessly. Why hasn't everyone switched to SSMs overnight?
It really does come down to a colossal wall of industry inertia. Dethroning the transformer is brutal because it has possessed a 7-year monopoly. Since 2017, the entire global tech ecosystem has been exclusively optimized for the exact mathematical operations of the transformer.
It's like the combustion engine problem. If an engineer invents a revolutionary new engine that is twice as efficient and runs on water, but every gas station, mechanic, supply chain, and manufacturing plant on Earth is built exclusively to handle gasoline engines, the new invention is going to face a massive uphill battle for adoption.
Precisely. Let's look at the hardware level. There are highly specialized low-level algorithms, the most famous being flash attention, that are written in CNIDA, explicitly designed to make the exact dot product matrix multiplication of the transformer run blazingly fast on NVIDIA silicon.
Oh, wow.
The hardware compilers themselves are tuned for it. When you introduce a radically different mathematical architecture like Mamba, you instantly lose all of those low-level optimizations. The theoretical efficiency of Mamba's linear math is bottlenecked because the physical GPU isn't optimized to execute those specific operations quickly. The AI community essentially has to rebuild the software infrastructure from the ground up for SSMs.
But the economic pressure to overcome that inertia is mounting. As companies demand million-token context windows to ingest entire code bases or corporate archives, the quadratic cost of the transformer will become unsustainable. Watching how these hybrid architectures evolve is crucial for developers who will be footing the bill for the API calls.
Absolutely. The architecture dictates the economics.
Okay, let's transition. We have an architecture, and it's pre-trained on internet data. But right now, it just wants to autocomplete sentences. We scrape the internet, we set up our GPU cluster, and we pump the raw text through the attention mechanisms for months. We have completed pre-training.
The model has learned the statistical relationships between billions of words.
Right. But if I take that raw, pre-trained base model and send it a prompt that says, write me a Python script to reverse a string, it will not write the script. It is highly likely to respond with something like, and other common interview questions asked by Google, because a base model is just a mathematically advanced autocomplete engine.
It just wants to predict the next statistical word on a web page.
Exactly. So how do we turn it into an application? How do we bridge the massive gap between an autocomplete engine and a helpful conversational assistant?
That bridging process is called post-training. The book offers a great conceptual distinction here. Pre-training is the grueling process of reading to acquire raw knowledge, token prediction. Post-training is the refined process of learning how to use and present that knowledge.
And what is truly staggering is the disparity in compute resources between the two phases.
Oh yeah, when OpenAI developed InstructGPT, which was the precursor to ChatGPT, they allocated 98% of their total compute budget purely to pre-training the base model. They spent only 2% of the compute on post-training.
That 2% unlocks the entire commercial viability of the product. That's wild. The first stage of this post-training is Supervised Finetuning, or SFT. Walk us through the mechanics of SFT.
In Supervised Finetuning, you start feeding the model random, unstructured web pages, and you start feeding it thousands of highly curated, human-annotated examples of dialogue. You provide the model with explicit instruction and response pairs. You write a prompt. Write a Python script to reverse a string. Then a human software engineer writes the perfect, highly structured response, complete with code blocks and explanations.
So mathematically, we are updating the model's weights to heavily favor this new pattern. We are telling the attention mechanism, when you see a query formatted as a question, do not pull from your statistical knowledge of Reddit forums where people argue. Instead, pull from your knowledge of how a helpful assistant formats a response.
Exactly. FFT teaches the model the format of conversation. It learns that it should be polite, that it should use bullet points, and that it should directly address the user's prompt. However, SFT introduces one of the most critical vulnerabilities in AI engineering, something developers must fundamentally grasp: the hallucination trap.
This is crucial. Let's dive deep into this. I've spent hours debugging microservices where an API fails silently and confidently returns a corrupted payload. LLM hallucinations feel exactly like that. Why does SFT cause hallucinations?
Because of the human element in the training loop. When companies hire human labelers to write those perfect responses for the SFT dataset, those labelers are intelligent humans with access to the internet. If you assign a label or prompt about an obscure historical event and they don't know the answer, what do?
They Google it.
They open a browser, Google the historical facts, synthesize them into a beautifully written, highly confident paragraph, and submit it as the training response.
Oh, wow. I see the architectural flaw. Because the human labelers might use external facts the base model never learned during pre-training. We are training the model to mimic the format and the authoritative tone of the human labeler. But the model itself might not know the facts.
Precisely. The model's weights are updated to perfectly mimic the structure, the vocabulary, and the confident tone of the human response. But when a user later asks the deployed model a similar question, the model applies that confident, authoritative tone to its own internal knowledge graph.
And if its internal knowledge is empty,
If its internal knowledge on that specific topic is sparse or non-existent, the model doesn't know how to say, "I don't know," because the human labeler never said, "I don't know." Instead, the model uses its training to generate words that statistically sound like a confident, factual answer. It mathematically invents plausible-sounding information. It hallucinates.
oh wow. It's basically like hiring a junior engineer who mimics the confident jargon of the senior devs, but they have no idea what the architecture actually is. They use words like idempotency, Kafka streams, and eventual consistency. They sound incredibly competent. But if you actually ask them to draw the system architecture on a whiteboard, they have no idea how the microservices connect. We are literally mathematically forcing the model to bluff. How do we fix that?
Well, the text references John Schulman, a co-founder of OpenAI, who provides a very sobering assessment. Fixing this is practically impossible with current technology.
Really? Impossible.
To completely eliminate this type of hallucination, engineers would need to perfectly map out exactly what external knowledge the human labeler injected into the response versus what the model natively knows deep within its billion-parameter matrix. We currently possess no diagnostic tools capable of definitively mapping the internal knowledge graph of a neural network. Therefore, we inevitably train them to bluff.
That is a critical reality check for any developer relying on an LLM for factual data extraction. But SFT gets the model talking formats, but it doesn't guarantee the model is safe or aligned with what users actually want. How do we prevent it from answering controversial or dangerous queries?
This requires the second, much more complex phase of post-training. Preference fine-tuning, most commonly implemented as reinforcement learning from human feedback, or RLHF. The goal of RLHF is to mathematically constrain the model so its outputs align with human preferences.
Which introduces an incredibly messy sociological problem into the math. Because human preference isn't a universal mathematical formula. People disagree on politics, religion, and culture.
Very much so.
The text specifically notes that models face dilemmas when asked about abortion, gun control, or the Israel-Palestine conflict. And to be completely clear here, as hosts, we're objectively explaining this. We're not taking a stance on any of these issues. But any answer to a controversial issue will upset someone. However, censoring the model too much makes it boring and drives away users.
You have a no-win scenario for the architects. They are attempting to embed a universal human morality into a linear algebra equation, and the universal human morality does not exist. They are forced to establish a baseline of safety, and they execute this using RLHF.
Let's break down how RLHF works. How do we actually translate human preferences into weight updates?
It is a sophisticated multi-step pipeline. First, you take your SFT-trained model and feed it a prompt. You configure the model to generate multiple different responses to that single prompt. You then hand those multiple responses to a human rater. The human's job is not to write a new response, but simply to rank them. Response A is the best, response B is okay, response C is toxic or unhelpful.
But we don't use this ranking data to train the main model directly, do we?
No, doing that would be incredibly inefficient. Instead, engineers use this massive data set of human rankings to train a completely separate secondary neural network called a reward model.
So we build an AI whose sole purpose is to judge the main AI.
Exactly. The reward model is trained to look at a prompt and a response and output a single scalar value, a number. A high number means a human would likely approve of the response. A low or negative number means a human would penalize it.
And then, using proximal policy optimization (PPO), you train the main model to generate responses that maximize those scores.
Right. We let the main model generate thousands of responses to various prompts. The reward model instantly grades every single response, assigning it a score. The PPO algorithm then takes those scores and mathematically tweaks the internal weights of the main model to encourage it to generate outputs that maximize the reward score and heavily penalize outputs that result in negative scores.
I love the internet meme the book mentions here. Pre-training gives us a Shoggoth, this terrifying, sprawling, multi-eyed alien monster of internet data from H.P. Lovecraft. SFT and RLHF are just us strapping a cardboard smiley face onto the monster to make it customer appropriate.
Yeah, the Shoggoth meme is perhaps the most accurate architectural diagram of an LLM in existence. RLHF isn't foolproof. It's an ambitious attempt to embed universal human preference into AI. But the underlying monster, the raw training data, is always there. RLHF does not delete the monster. PPO does not erase the toxic or biased data. It simply mathematically suppresses those pathways.
Which explains why users can invent jailbreaks. By crafting highly complex, convoluted prompts, users bypass the cardboard mask, tricking the attention mechanism into ignoring the RLHF penalties and accessing the raw Shoggoth underneath.
Precisely. The safety alignment is fragile because it is imposed on top of the model, not baked into the foundational data.
Okay, we have traversed the entire pipeline. We've aligned the model, it's ready. You, the backend engineer, make an API call. What happens in that absolute final split second to generate the text, and why is it sometimes inconsistent?
To understand the final unpredictability, we have to examine the very last layer of the transformer architecture, often called the unembedding layer.
Right.
After the prompt has passed through all the layers of multi-headed attention, after the queries, keys, and values have been blended and processed, the model produces a final, massive vector of numbers representing the context. But an API cannot return a vector of numbers to a user expecting text. We must translate the math back into English.
How does the unembedding layer do that translation?
The unembedding layer maps that final vector against the model's entire vocabulary. It generates raw scores, called logits, for every single possible word it knows. It then passes those logits through a final softmax function, converting them into token probabilities.
Okay, probabilities.
Right. The model never definitively states the next word is server. Instead, it generates a probability distribution. It calculates, given the context, there is a 70% chance the next word is server, a 20% chance it is database, a 9% chance it is application, and a 1% chance it is banana.
And this process is called sampling. This is the exact moment the model chooses the next word.
Yes. Because it relies on token probabilities rather than a rigid, hard-coded path, this generation setting is exactly what dictates baffling behaviors, like why a model can give you two completely different answers to the same question, or why it hallucinates.
So as a back-end dev, you have to stop thinking of this as a pure deterministic function. It's more like a highly educated roulette wheel. You're rolling a weighted die for every single syllable.
Exactly. You're managing probabilities, not certainties. But tweaking these generation settings is a cheap, easy way to significantly boost the model's performance for specific applications. The most common sampling variable is temperature.
Let's break down mechanically what temperature does to those probabilities.
Temperature directly manipulates the softmax distribution before the model rolls the dice. If you set the temperature to 0, you remove the randomness entirely. The sampling algorithm becomes deterministic. It will perform an argmax operation, simply selecting the token with the highest probability every single time. If server is at 70%, it picks server.
Which sounds perfect for back-end code generation or data extraction. We want predictability.
It is highly effective for rigid tasks. But if you apply a temperature of 0 to creative writing or conversational dialogue, the output becomes incredibly robotic, repetitive, and dull. It traps the model in statistical loops. Human language requires variance. To introduce that variance, you raise the temperature. Raising the temperature mathematically flattens the probability distribution.
So if I push the temperature to 1.0, that 70% chance for server might drop to 40%, and that 1% chance for banana might rise to 10%.
Exactly. You are introducing randomness, allowing the model to occasionally pick less statistically obvious words, which makes the text feel more natural and creative. But if you raise it too high, the distribution flattens completely, and the model devolves into generating pure, incomprehensible gibberish.
And temperature isn't the only lever. The book discusses top K and top sampling. How do those constrain the roulette wheel?
Talk is a hard cutoff. If you set top K to 50, The model looks at the probability distribution, isolates the top 50 most likely words, and completely ignores the rest of the vocabulary, redistributing the probability only among those 50. It prevents the model from ever picking that 1% banana anomaly.
And top.
Top pick, also known as nucleus sampling, is a dynamic cutoff based on cumulative probability. If you set top 8 to 0.90, the model ranks the words by probability and starts adding them to a pool until the combined probability of the pool reaches 90%. It only samples from that dynamically sized pool.
So by carefully tuning temperature, top cake, and top in your API requests, a back-end engineer can drastically alter the behavior of the model without changing the model itself. Turn the temperature down for JSON extraction. Open up top for writing marketing copy.
Exactly.
But what if the task is highly complex, like solving a math problem or writing a complex algorithm where a single bad roll of the dice ruins the entire output?
That brings us to one of the most powerful inference techniques covered in the text: test time compute. Instead of forcing the model to generate one single perfect path, you leverage the probabilistic nature of the model. You generate multiple different responses to the same prompt in parallel. Because of the sampling variance, the model will take different logical paths.
Right. And then you use a secondary verification process, either another model or an automated testing framework, to evaluate the multiple outputs and select the best one. You are trading extra API compute costs for a massive increase in reliability and reasoning accuracy.
It's an entirely new paradigm of software architecture. We are building systems to manage and corral probability.
Wow. Let's zoom out and synthesize this incredible journey. We built this deep dive specifically for the back-end engineers who are suddenly tasked with integrating these alien systems. We started by exploring the massive economic shift that forced the industry away from custom, task-specific machine learning models, pushing developers to build on top of massive, pre-trained foundation models.
We examined the terrifying reality of the data foundation, how these models are indiscriminate statistical mirrors of a web scraping process, filled with toxicity and intentional data poisoning, making downstream curation essential. And we navigated the licensing minefield, detailing why the difference between Meta's restricted open weights and Google's Apache 2.0 license can dictate the survival of a startup.
Then we opened up the engine block. We broke down the failure of the old sequential RNNs and how the transformer's prefill and decode phases revolutionized processing. We dissected the attention mechanism, translating the linear algebra of queries, keys, and values into the probabilistic database blend that allows the model to deeply understand context using dot products and softmax.
We highlighted the architectural vulnerabilities, specifically the quadratic memory bloat of the KV cache that makes large context windows exponentially expensive. We explored the frontier of state-space models, looking at Mamba's linear scaling and Jamba's mixture of experts hybrid approach, while acknowledging the massive hardware optimization inertia keeping the transformer on the throne.
We then charted the post-training pipeline. We saw how supervised fine-tuning teaches the model to format its output, inadvertently introducing the hallucination trap by mathematically forcing the model to bluff like an overconfident junior engineer. We explored how RLHF attempts to align the model with human preferences using a reward model in PPO, effectively strapping a cardboard smiley face onto the raw internet shoggoff.
And finally, we analyzed the unembedding layer, demonstrating how token probabilities and sampling techniques like temperature and top-up dictate the final unpredictable behaviors engineers must manage in production.
It is a staggering stack of mathematical abstractions. Understanding these underlying mechanics is what separates an engineer who blindly makes API calls from an architect who can actually build robust, scalable AI systems.
Very well said.
As we wrap up this deep dive, I want to leave you with a final puzzle, a conceptual problem to chew on as you design your next application. We talked extensively about how our primary method of making these incredibly powerful models safe RLHF relies entirely on training them with PPO to maximize a reward score. And that reward score is generated by a secondary AI that was trained on what human raters prefer to hear.
Right.
But think about the philosophical implications of that architecture. If our primary method of making these powerful models safe relies entirely on training them to maximize a reward score based on what human raters like to hear, are we actually building systems that seek objective truth? Or are we meticulously programming them to be the ultimate sycophants crowd pleasers designed to mirror our own biases and tell us exactly what we want to hear, whether it is the factual truth or not?
It's a sobering thought.
As we move further away from deterministic code and deeper into this new probabilistic paradigm, are we ever going to get back to the clean diagnostic precision of the X-ray machine? Or are we destined as an industry to simply keep swimming in the murky, unpredictable waters of statistical sampling? Something to think about the next time you write an API request, adjust the temperature, and hit execute.